Look up tonight. If the sky is clear, if the city lights are dim enough, you'll see them. Stars. Thousands of them. Maybe millions if you're somewhere truly dark. Points of light that have guided sailors and dreamers and lovers for as long as humans have existed. They seem eternal, don't they? They were there before you were born. They'll be there after you're gone. Your great-great-grandparents saw the same Orion, the same Big Dipper, the same Milky Way stretched across the summer sky. Eternal, unchanging, forever. But I need to tell you something. Something that scientists have known for a century, but that most people never truly absorb. Something that changes everything about how we see our place in the cosmos. Every star you see tonight will die. Every single one. Not in some abstract philosophical sense, not as a metaphor, literally, physically. The nuclear fires that make them shine will exhaust their fuel, and the light will go out, one by one, star by star, until there are none left. And then, the universe will go dark, forever. Tonight, we're going to take a journey together, the longest journey possible. We're going to travel forward in time, not millions of years, not billions of years, but trillions and quadrillions, and numbers so large they lose all meaning. We're going to watch the stars die. We're going to witness the end of light itself. We're going to see what happens when the last ember of the last star fades into the infinite dark. And then, we're going to see what comes after. This is the story of the death of everything. And somehow, it's also a story about why right now, this moment, this breath, this heartbeat, matters more than you ever imagined. Let's begin. Here's something that will haunt you once you truly understand it. The universe is dying. Not quickly, not soon by any human measure, but inevitably, irreversibly. The cosmos as we know it, full of light and heat and energy and life, is a temporary state, a brief flicker, a passing phase in an eternity of darkness. We live in a very special time. Cosmologists call it the stelliferous era, the age of stars. It began about 200 million years after the Big Bang, when the first stars ignited and flooded the universe with light. And it will end in about 100 trillion years, when the last stars burn out. 100 trillion years. That sounds like forever, doesn't it? It's not. The universe will exist for so much longer than that, so incomprehensibly longer, that the stelliferous era, this entire age of stars that includes every moment of every life that has ever existed or ever will exist, represents the tiniest sliver of cosmic history. Imagine the entire future lifespan of the universe as the distance from New York to Los Angeles. The age of stars, everything we know, everything we are, every civilization that will ever arise, every thought that will ever be thought, fits within the first step out your front door. Less than that, the first inch. After that first inch, darkness. For all the remaining miles, all the remaining distance stretching to the Pacific Ocean and beyond, darkness. This isn't speculation. This isn't science fiction. This is physics, thermodynamics, the fundamental laws that govern reality. And those laws are clear. Everything runs down. Everything decays. Everything ends. Even the stars. The countdown has already begun. Right now, as you listen to these words, stars are dying. Somewhere in the universe, actually in many places in the universe, massive stars are collapsing. They've burned through their hydrogen. They've fused helium into carbon, carbon into oxygen, oxygen into silicon, silicon into iron. And when they hit iron, the fusion stops. There's no more energy to be extracted. And in that moment, the star dies. Sometimes quietly, fading into a dense white dwarf, sometimes violently, exploding as a supernova so bright it outshines entire galaxies. Sometimes, catastrophically, collapsing into a black hole from which nothing, not even light, can escape. Right now, as you lie there, somewhere a star is taking its final breath. And it's not being replaced. Well, not exactly. Stars are still being born. In vast clouds of gas and dust, gravity is pulling material together, igniting new nuclear fires. New stars are waking up right now, somewhere in the cosmos. But here's the thing. The universe is running out of gas. The raw material for making stars, hydrogen mostly, is being used up, converted into helium, into heavier elements, into stellar corpses that will never burn again. And while the universe is unimaginably vast, it's also finite. There's only so much hydrogen, only so many stars that can ever be made. We're past the peak. The rate of star formation has already declined dramatically from its height billions of years ago. The universe is making fewer stars now than it used to, and that trend will continue, accelerating until star formation stops entirely. The last star that will ever be born has perhaps already been born, or perhaps it will be born tomorrow, or 1 billion years from now. But whenever it ignites, no more will follow. And then the countdown truly begins. What does it actually mean for a star to die? Let's start with our own sun. Right now, the sun is a middle-aged star, about 4.6 billion years old, roughly halfway through its life. It's a comfortable, stable yellow dwarf, fusing hydrogen into helium in its core, producing the heat and light that makes life on Earth possible. But it won't last. In about 5 billion years, the sun will begin to change. It will run low on hydrogen in its core. The fusion that has sustained it for billions of years will sputter and slow. And when that happens, gravity, always pulling inward, will start to win. The core will contract, compress, heat up. And that heat will cause the outer layers of the sun to expand, to swell, to grow. The sun will become a red giant. It will expand past the orbit of Mercury, past Venus. It will grow so large that it will nearly reach Earth's orbit, perhaps even engulf our planet entirely.
The oceans will boil away. The atmosphere will be stripped into space. The rocks themselves will melt. Everything humanity ever built, every monument and city and work of art, every fossil of every creature that ever lived, will be vaporized, erased, as if we never existed.
But the sun won't survive this expansion. Red giants are unstable. The sun will pulse and shudder, throwing off its outer layers in vast shells of glowing gas. These shells will expand outward, cooling as they go, creating what astronomers call a planetary nebula, one of the most beautiful objects in the universe. And at the center, all that will remain is the sun's core, a small, dense, incredibly hot object about the size of Earth, but containing half the sun's original mass, a white dwarf. It won't be fusing anymore. It won't be producing new energy. It will simply be glowing with the residual heat of its collapse, slowly cooling over billions and trillions of years, fading, dimming, until eventually it goes dark entirely, becomes a black dwarf, a cold, dead cinder floating through eternal night. That's the fate of our sun. That's the fate of most stars.
But not all stars die quickly. Some stars are different. The smallest stars, red dwarfs, are the misers of the cosmos. They burn their fuel so slowly, so carefully, that they can last for trillions of years. Think about that. Our sun will live for about 10 billion years total, a respectable lifespan. But a red dwarf can last for 10 trillion years, 1,000 times longer. These dim, cool, unassuming little stars, they're the survivors. When our sun has long since burned out, when the great blue giants and yellow stars like ours are ancient memories, the red dwarfs will still be shining, faintly, stubbornly, clinging to existence. They make up about 70% of all the stars in the universe, and they will be the last stars to die. The very last star that will ever shine will almost certainly be a red dwarf. Some dim little ember at the edge of a dead galaxy, surrounded by the corpses of brighter stars, alone in the growing darkness. And one day, even that star will exhaust its fuel. Its fusion will stop. Its light will fade. And the stelliferous era, the age of stars, will end. The universe will never be bright again.
The promise of this journey. I know this sounds bleak. I know it might even seem cruel to contemplate such things. What's the point of thinking about events so far in the future that they have no bearing on our lives? But there is a point. Several points, actually. First, understanding the full timeline of the universe puts our existence into perspective. It shows us just how precious and improbable our moment is. Right now, stars are shining. Right now, planets are warm. Right now, life exists and thinks and wonders. That won't always be true. Second, even in the dying of the light, there is beauty. The universe's long fade into darkness is not just an ending, it's a transformation. Strange and wonderful things will happen in those distant epochs, possibilities we can barely imagine. The far future raises profound questions about meaning, purpose, and what it truly means to exist. If everything ends, what matters? If nothing lasts, why does anything mean anything? These are the questions we'll explore tonight. So settle in, get comfortable, let your breath slow and your mind open. We're going to travel forward in time together, past the death of our sun, past the death of all suns, past the end of light itself. And we're going to see what's waiting in the dark. Before we journey into the darkness, let's appreciate the light. Right now, you exist in the most glorious era the universe will ever know. The stelliferous era, the age of stars. Look around at the cosmos as it exists today, and you're seeing something extraordinary, something rare, something that will not last. Hundreds of billions of galaxies, each containing hundreds of billions of stars, light everywhere, energy pouring out across the electromagnetic spectrum, nebulae glowing in rainbow colors, supernovae outshining entire galaxies, quasars blazing at the hearts of distant realms. The universe is alive with light. But it wasn't always this way, and it won't be this way for much longer, not by cosmic standards. The dawn of light. For the first 200 million years after the Big Bang, the universe was dark. Hard to imagine, isn't it? All that matter, all that energy, all that potential, and no stars. Just clouds of hydrogen and helium drifting through expanding space, cooling, clumping, waiting. Cosmologists call this period the Dark Ages. And then, something magical happened. In certain regions where the gas was slightly denser than average, gravity began to win. Material started falling together. Clouds contracted, compressed, heated up. And at some point, in the core of one of these collapsing clouds, the temperature and pressure became high enough for hydrogen nuclei to fuse into helium. Nuclear fusion ignited. A star was born. The first star. We don't know exactly when or where. We don't have a photograph or a precise date, but somewhere in that dark universe, about 200 million years after the Big Bang, light appeared. And then more lights and more. The Dark Ages ended. The stelliferous era began. And for the next 100 trillion years or so, the universe would shine. The Golden Age. We're living in what you might call the Golden Age of the Golden Age. Star formation peaked about 10 billion years ago. That was the universe's most productive period, when new stars were being born at the highest rate in cosmic history. Galaxies were colliding, gas was being compressed, stellar nurseries were working overtime. Since then, the rate has declined. Today, stars are still being born, but at a fraction of the peak rate. The raw materials are running low. Galaxies have used up much of their available gas. The universe is becoming more sedate. But there's still tremendous activity. In our own galaxy, the Milky Way,
New stars are born every year. In vast stellar nurseries like the Orion Nebula, thousands of baby stars are taking their first breaths right now. Hot, blue, brilliant, they're joining the cosmic community, adding their light to the great symphony. And across the observable universe, roughly 400 million stars are born every day. 400 million every single day. It sounds like abundance, like infinity, like the stars will never stop coming. But remember, stars also die, hundreds of millions of them every day. And the birth rate is falling, while the death rate, well, eventually the deaths will overwhelm the births. The balance will tip, the decline will accelerate, and one day the last star will be born.
How stars live and die. Let's talk about stellar lifetimes, because not all stars are created equal. The most massive stars, the blue giants, the supergiants, the hypergiants, are the cosmos's most spectacular objects. They're tens or even hundreds of times more massive than our sun. They shine with the light of millions of suns. They're so luminous they can be seen across intergalactic distances. But they pay for that brilliance with their lives. Massive stars burn through their fuel at a prodigious rate. A star 10 times the mass of the sun doesn't live 10 times as long. It lives only a tiny fraction as long. Perhaps 10 million years, maybe 20 million. That sounds like a lot, but in cosmic terms, it's nothing. Our sun has already lived 4.6 billion years. These massive stars come and go in the blink of an eye. And when they die spectacularly. Supernovae. The most powerful explosions in the universe. For a brief moment, weeks, sometimes months, a single dying star can outshine its entire galaxy. Billions of stars, and one explosion matches them all. In that explosion, elements are forged. Carbon, oxygen, nitrogen, iron, gold, uranium. The building blocks of planets and people are cooked in the furnace of a dying star and scattered across space. We are made of dead stars. The calcium in your bones, the iron in your blood, the oxygen in your lungs, it all came from stars that died before our sun was born. Medium-sized stars, like our sun, live longer, billions of years. They're the steady, reliable citizens of the galaxy. Not too bright, not too dim. Stable enough for planets to form around them, for life to potentially arise. But they too will die. They too will expand into red giants, shed their outer layers, collapse into white dwarfs, and slowly fade over eons until their light goes out entirely. The red dwarf inheritance. And then there are the red dwarfs. The smallest true stars, the dimmest, the coolest. Red dwarfs make up about 70% of all stars in the Milky Way. They're everywhere. Proxima Centauri, the closest star to our sun, is a red dwarf. TRAPPIST-1, home to that famous system of 7 Earth-sized planets, is a red dwarf. They're so dim that you can't see a single one with the naked eye, even though they vastly outnumber all other star types combined. But here's the thing about red dwarfs. They're survivors. They burn their fuel so slowly, so incredibly slowly, that they can live for trillions of years. Not billions, trillions. A red dwarf born today could still be shining when the universe is 10 trillion years old, when our sun is a cold black dwarf, when the Milky Way has merged with Andromeda and become a giant elliptical galaxy,
when almost everything we know has changed beyond recognition, that little red dwarf will still be there, still burning, still shining. Faintly. Stubbornly. Alone. The last galaxies. As we move forward in time, the universe changes. Galaxies, which today are scattered across the expanding cosmos, will eventually become isolated islands. You see, the universe is expanding. Space itself is stretching, carrying galaxies apart from each other. Today, we can see galaxies billions of light years away. We can study them, photograph them, analyze their light. But that won't always be true. The expansion of the universe is accelerating, driven by dark energy, that mysterious force we still don't fully understand. And as it accelerates, distant galaxies are moving away from us faster and faster. Eventually, they'll be moving away faster than light. Not that they're traveling through space faster than light, that's impossible. But space itself is stretching so fast that their light can no longer reach us. One by one, galaxies will disappear beyond our cosmic horizon. By about 100 billion years from now, everything outside our local group of galaxies, everything beyond the Milky Way, Andromeda, and a few dozen smaller companions, will be invisible. Their light will never reach us. It will be as if they never existed. And our local group, meanwhile, will have merged. The Milky Way and Andromeda are actually moving toward each other. In about 4.5 billion years, they'll collide and merge into a single giant elliptical galaxy. Astronomers have already given it a name, Milkdromeda, or sometimes the Milky Way-Andromeda collision, the Milkomeda. This new megagalaxy will absorb the other members of the local group, and then it will be alone. A single galaxy containing several trillion stars floating in a vast, dark emptiness. No other galaxies visible in any direction, just darkness stretching to infinity. The slowing birth rate. As the eons pass, star formation will slow. The gas that feeds stellar nurseries will be used up, converted into stars, into stellar remnants, into diffuse clouds too thin to collapse. The raw material for new stars will become increasingly scarce. New stars will still be born, but less frequently. The average age of stars in the galaxy will increase. The proportion of red dwarfs, those ancient survivors, will grow. The bright blue giants, which live fast and die young, will become increasingly rare. The galaxy will grow dim. Its color will shift from the vibrant mix we see today toward the red end of the spectrum. Red stars, old stars, dying stars. And one day, the last star will be born. We don't know exactly when. The calculations depend on complex factors: how gas is recycled, how efficiently stars form, how dark energy affects the available material. But estimates suggest that significant star formation will cease within about 1 to 100 trillion years. After that, no new stars. Ever. The last starlight. Once star formation stops, it's just a matter of waiting. The existing stars will continue to burn, but one by one, they'll exhaust their fuel and die. The massive stars will go first. They always do. Then the medium-sized stars. Then the smaller ones. The red dwarfs, those ancient survivors, will persist the longest. A red dwarf born near the end of star formation could continue burning for another 10 trillion years, perhaps longer. Burning hydrogen so slowly, so carefully, that it stretches its fuel across eons that dwarf the current age of the universe. But even red dwarfs have limits. Eventually, even the most frugal star will run out of fuel. Its fusion will sputter and stop. Its light will fade. And when the very last red dwarf burns out, the stelliferous era will end. No more stars, no more nuclear fires, no more natural light in the entire universe. The age of stars, which includes every moment of every life that has ever existed, will be over, and the long darkness will begin. What we have right now. So here we are, right now, this moment, this breath. You're living in the stelliferous era, the golden age, the time when the universe is bright and warm and alive. You're made of atoms that were forged in stars. You're seeing by light that traveled from the sun. You're warmed by nuclear fires burning 93 million miles away. And you're conscious. You're aware. You know that stars exist, that they're born and die, that the whole show is temporary. You can contemplate your own existence in the context of cosmic time. That makes us incredibly special. In the far future, when the stars are gone, when the universe is cold and dark, there may be nothing. No one to remember that the stars ever shone, no consciousness to contemplate the darkness. But right now, we are here, thinking about it, wondering about it, appreciating maybe for the first time just how extraordinary this moment really is. Breathe that in. The light of stars, the warmth of existence, the miracle of awareness. It won't last forever, but it's here now. And that's enough. The last red dwarf has burned out. Try to picture this moment. For over 100 trillion years, there was always at least one star shining somewhere. Always some nuclear fire burning, always some light pushing back against the darkness. And now, nothing. The final fusion reaction has completed. The last hydrogen atom has been converted. The last photon of starlight has been released. Darkness. Not the darkness of night, where the sun is merely hidden behind the earth. Not the darkness of space between galaxies, where distant lights still twinkle if you look hard enough. True darkness. Absolute. Permanent. The universe will never naturally produce light again.
Welcome to the degenerate era. It's an unsettling name, isn't it? But it's not a moral judgment. It's a physics term. It refers to degenerate matter, the exotic compressed material that makes up the stellar corpses left behind when stars die. This era begins roughly 100 trillion years after the Big Bang. It will last until about 10 to the 40th years from now. That's a 1 followed by 40 zeros, incomprehensibly long. And during all that time, no stars, no light, just the slow decay of what remains. A universe of corpses. So what does remain? When the stelliferous era ends, the universe isn't empty. Far from it. It's filled with the remnants of trillions upon trillions of dead stars. 3 types of corpses dominate this dark landscape. First, white dwarfs. These are the remains of stars like our sun. Dense, compact spheres, about the size of Earth, but containing roughly half the mass of the original star. When our sun dies billions of years from now, its core will become a white dwarf. White dwarfs don't produce energy through fusion. Their nuclear fires are extinguished. But they're incredibly hot when they form, hundreds of thousands of degrees, and they glow with that residual heat. The thing is, they cool down. Slowly, agonizingly slowly, but inevitably.
A white dwarf radiates its heat into space, and as it does, it grows dimmer, cooler, fainter. In the degenerate era, white dwarfs that were once brilliant are now barely glowing, faint red embers, then infrared sources invisible to any eye, then cold. Eventually, every white dwarf will cool to the temperature of the surrounding space, just a few degrees above absolute zero. When that happens, they become black dwarfs, cold, dark, dead. The universe has never been old enough to produce a true black dwarf. It takes so long for white dwarfs to cool completely that none have finished the process yet. The oldest white dwarfs in the universe are still glowing, still warm. But in the degenerate era, black dwarfs will be everywhere. Trillions of them, quadrillions, dark spheres of crystallized carbon, invisible against the infinite black, floating in silence.
Neutron stars, the second type of corpse. A neutron star is the ultimate in compression, the core of a dying star crushed so intensely that electrons and protons are forced together into neutrons. The entire mass of the Sun squeezed into a sphere just 15 miles across. A teaspoon of neutron star material would weigh billions of tons. When they're born, neutron stars are incredibly hot and often spinning rapidly, hundreds of times per second. They emit beams of radiation from their magnetic poles. If those beams sweep past Earth, we see them as pulsars, cosmic lighthouses flashing with clockwork precision. But, like everything else, neutron stars run down. They spin slower and slower. Their magnetic fields weaken. Their heat radiates away into the void. In the degenerate era, neutron stars are cold and dark, no longer spinning fast enough to emit radiation, no longer hot enough to glow, just dense balls of degenerate matter, 15 miles of compressed neutrons sitting in eternal silence.
Black holes. And then there are the black holes. The most massive stars, when they die, don't leave behind white dwarfs or neutron stars. Their gravity is too strong. Nothing can stop the collapse. The core falls inward, crushing itself into a singularity, a point of infinite density, where our understanding of physics breaks down completely. And around that singularity forms an event horizon, a boundary from which nothing, not even light, can escape. Black holes. In the degenerate era, black holes are everywhere. Not just the stellar mass black holes left behind by individual supernovae, but the supermassive black holes at the centers of galaxies. These monsters contain millions or billions of times the mass of our Sun. They've been growing for billions of years, swallowing stars and gas and anything that wanders too close. When the stars go out, the supermassive black holes remain. In fact, they become the dominant objects in the universe. Entire dead galaxies, now dark and cold, orbit around their central black holes. Trillions of stellar corpses, black dwarfs, neutron stars, smaller black holes, circling in the darkness around these gravitational monarchs. No light, no heat, just gravity holding everything together in the dark. The quality of darkness. What would it be like to exist in the degenerate era? Imagine waking up in that universe. You open your eyes and nothing. Absolute black. Not because your eyes are closed, but because there's no light to see. You might be floating in space between black dwarfs, surrounded by trillions of them, and you'd never know. They emit nothing. They reflect nothing. They're invisible. The only way you'd know they were there is by their gravity, by the subtle tug of passing masses, by the way space curves around them. If you had incredibly sensitive instruments, devices that could detect infrared radiation at the lowest temperatures, you might be able to sense them. Faint signatures just barely above absolute zero. Whispers of warmth in an ocean of cold. But to any natural sense, darkness. and cold. The temperature of the universe in this era approaches absolute zero. Not quite there, we'll talk about that more later, but close. A few billionths of a degree above the coldest possible temperature. Cold beyond imagining. Cold beyond anything that exists today. The cosmic microwave background, that faint afterglow of the Big Bang that currently fills the universe with a temperature of about 2.7 Kelvin, will have cooled to almost nothing. The universe will be as cold as physics allows. Strange chemistry in the dark. But here's something remarkable. Even in this darkness, even in this cold, things still happen. They happen slowly, unimaginably slowly, but they happen. Black dwarfs, for instance, will continue to evolve. The carbon and oxygen in their cores will slowly, over timescales that dwarf anything we've discussed, undergo nuclear reactions. Not fusion exactly, something different. Quantum tunneling. In quantum mechanics, particles can occasionally tunnel through barriers they shouldn't be able to cross. It's a random process, governed by probability. Most of the time, the particle stays where it is, but occasionally, rarely, it makes it through. On the timescales of the degenerate era, even incredibly rare events become inevitable. Carbon nuclei will tunnel together, fusing into heavier elements despite the cold. Iron will form in the cores of black dwarfs, atom by atom, reaction by reaction, over incomprehensible stretches of time. This process will take about 10 to the 1,500 years. That's a 1 followed by 1,500 zeros. We have no words for numbers this large. They exceed not just human comprehension, but perhaps the comprehension of any mind that could exist. And yet, it will happen. Eventually, if nothing else intervenes, black dwarfs will transform their cores into iron, the most stable element, the endpoint of nuclear evolution. And then, iron stars and beyond. Once a black dwarf's core is iron, another process begins, an even slower one. The iron core will eventually collapse, not through fusion. Iron can't fuse to release energy, but through a process called pycnonuclear fusion. Quantum tunneling allows iron nuclei to merge, building heavier elements, releasing a tiny amount of energy. And ultimately, the black dwarf will shrink. Over time scales of perhaps 10 to the 1,500 years or more, the iron core will compress further and further. The black dwarf will slowly collapse, growing denser. What happens at the end? There are several possibilities. If the black dwarf is massive enough, it might eventually collapse into a neutron star, or even, eventually, a black hole. If it's less massive, it might undergo a different fate, a kind of ultra-slow-motion supernova, a final explosion, releasing the energy built up over cosmic ages, blowing the star apart. Either way, the black dwarfs won't last forever. Nothing lasts forever. The loneliness of objects. During the degenerate era, something else is happening. The objects in the universe are drifting apart. Remember those dead galaxies with their trillions of stellar corpses orbiting central black holes? Over time, gravitational interactions cause changes. Sometimes two dead dwarfs pass close to each other. Their gravity interacts. One gets flung outward, the other falls inward. This process, called gravitational relaxation, slowly reshuffles the dead galaxy. Over trillions of years, most objects are ejected, flung out of the galaxy entirely, sent drifting through intergalactic space, alone. The dead galaxy evaporates. Most of its mass is lost. Black dwarfs, neutron stars, wandering through the void with no home, no neighbors, nothing but infinite emptiness in every direction. A small fraction falls inward, captured by the central supermassive black hole, swallowed. By about 10 to the 19 to 10 to the 20 years, most galaxies will have evaporated. The universe will no longer contain galaxies at all, just scattered objects drifting through darkness and black holes slowly consuming what falls their way. A universe fading. The degenerate era is the long twilight. No stars burning, no light shining, just the slow cooling of stellar corpses, the slow decay of structures, the slow drift of objects through empty space. It lasts for unimaginable spans of time. From about 10 to the 14 years when the last stars die, to about 10 to the 40 years when black holes begin to dominate. That's hard to grasp. The current age of the universe, 13.8 billion years, is nothing compared to the degenerate era. It's like comparing the blink of an eye to the age of the Earth. During all that time, the universe is dark, cold, silent. But it's not empty. Not yet. The black dwarfs are still there, the neutron stars, the black holes. Matter still exists, and as long as matter exists, something remains. But even matter won't last forever, because eventually even the black holes will die, and when that happens, the universe enters its final era.
The black dwarfs have evaporated. The neutron stars have been scattered or swallowed. What remains? Black holes. In the black hole era, spanning from roughly 10 to the 40th years to 10 to the 100 years after the Big Bang, black holes are the only significant objects left in the universe. Not just stellar mass black holes, the corpses of individual massive stars, but supermassive black holes. The monsters that once anchored galaxies, containing millions, billions, sometimes tens of billions of solar masses. They've grown over the eons, swallowing every black dwarf and neutron star that fell within their reach, growing larger with each meal. And now, they reign supreme. Lords of nothing. Picture a supermassive black hole in this era. It floats in absolute darkness. There are no stars to illuminate it, no accretion disk of infalling matter to glow with friction, no jets of radiation erupting from its poles, just the black hole itself. An event horizon, a spherical boundary in space-time, marking the point of no return. Cross that boundary and you can never escape. Not even light can climb back out. Inside the horizon, the singularity, a point of infinite density where space-time itself breaks down, where our physics has no answers. The black hole is invisible, truly invisible. It emits no light, it reflects no light. There is no light to emit or reflect. You could be right next to a black hole containing 1 billion suns and you'd see nothing, feel nothing, until you got close enough for the tidal forces to matter. Then you'd feel the pull. Gravity warping space around you, pulling your feet, if you fell feet first, harder than your head, stretching you out. Physicists call it spaghettification. You'd be pulled into a thin strand, stretched toward the singularity, then gone. Added to the black hole's mass, making it infinitesimally larger. Hawking's discovery. For a long time, scientists thought black holes were eternal. Once formed, a black hole would exist forever. It could only grow, never shrink, the ultimate endpoint of matter. But then came Stephen Hawking. In 1974, Hawking made a stunning discovery. Using the principles of quantum mechanics applied near a black hole's event horizon, he showed that black holes must emit radiation, Hawking radiation. Here's the basic idea. The universe, at its smallest scales, is not empty. Even in a perfect vacuum, quantum mechanics predicts that particle-antiparticle pairs are constantly popping into existence, existing for an unimaginably brief moment, then annihilating each other.
These virtual particles are everywhere, all the time. But near a black hole's event horizon, something strange can happen. A virtual pair might appear right at the edge of the horizon. One particle falls in, the other escapes. The escaping particle is real. It carries energy away from the black hole. And here's the key. That energy has to come from somewhere. It comes from the black hole itself. The black hole loses a tiny bit of mass for every particle that escapes. It shrinks, imperceptibly, incredibly slowly, but it shrinks. Hawking radiation means that black holes are not eternal. They evaporate. But don't get too excited. This process is unbelievably slow. The rate of Hawking radiation depends on the black hole's mass. The more massive the black hole, the slower it evaporates. A stellar mass black hole, say 10 times the mass of our Sun, would take about 10 to the 67 years to evaporate. That's a 1 followed by 67 zeros. A supermassive black hole containing 1 billion solar masses, about 10 to the 100 years. These timescales are beyond comprehension. The current age of the universe, 13.8 billion years, is 1.38 times 10 to the 10th years. The evaporation time for a supermassive black hole is 10 to the 100. That's not even comparable. The ratio between them exceeds any number we've ever used for anything. But time, in the far future, is essentially infinite, and eventually, 10 to the 100 years will pass. The final flash. As a black hole evaporates, it shrinks. And here's something interesting. The smaller it gets, the faster it evaporates. Hawking radiation is inversely related to mass. A small black hole evaporates faster than a large one, much faster. This means that a black hole's evaporation accelerates at the end. After spending unimaginable eons slowly, imperceptibly shrinking, a black hole's final moments are rapid. In the last second of its existence, a black hole about the mass of a small asteroid will emit a burst of energy equivalent to a nuclear bomb. For a brief instant, a flash in the eternal darkness, there is light. The black hole converts its remaining mass into radiation, exploding outward in a final burst of gamma rays and particles. And then, it's gone. The black hole has evaporated completely. There is nothing left. Imagine being there to witness this. The universe has been dark for 10 to the 100 years. No stars, no light, nothing but black holes drifting through infinite emptiness. And then, a flash. The last supermassive black hole, containing billions of solar masses, finally evaporates. It releases a burst of radiation that for a moment illuminates the void. The last light the universe will ever produce. And then, darkness again. Permanent. Final. What's left? When the last black hole evaporates, what remains? Almost nothing. The radiation from Hawking evaporation will spread out into the expanding universe, diluting, redshifting, cooling. Some particles will remain. Electrons, positrons, photons, neutrinos, scattered across space so thinly that the average distance between particles is greater than the current size of the observable universe. Imagine that. One electron here, another electron there, and the distance between them is billions of light years. That's how empty the universe becomes. No structures, no objects, no concentration of matter anywhere. Just particles, drifting, alone, in infinite darkness. The temperature of oblivion. And it's cold. So cold. The universe has been expanding for 10 to the 100 years. The cosmic microwave background, which currently has a temperature of about 2.7 Kelvin, has cooled to a temperature so close to absolute zero that we can barely express it. 10 to the negative 30 Kelvin. A decimal point, 29 zeros and then a 1. Nothing in the current universe is anywhere near that cold. The coldest experiments ever conducted on Earth reach about 10 to the negative 12 Kelvin. We're talking about temperatures a billion times colder than that. At these temperatures, almost nothing happens. Chemical reactions? Essentially impossible. The particles don't have enough energy to interact. Movement? Only the faintest quantum fluctuations. Time itself still passes technically, but with nothing happening, does it even mean anything? The hierarchy of evaporation. The black hole era doesn't end all at once. Different black holes evaporate at different rates. The smallest black holes, those formed from stellar collapse, evaporate first. They might last only 10 to the 67 years. Then the intermediate mass black holes, perhaps thousands or millions of solar masses. Then the supermassive black holes, billions of solar masses, taking up to 10 to the 100 years. Each evaporation is a momentary flash in the darkness, a brief reminder that something still exists, and then silence again. During the black hole era, these flashes are the only events, the only breaks in the monotony. An evaporation here, another there, separated by spans of time that exceed all of previous cosmic history, until finally, the last one, the very last black hole, the very last object in the universe. It evaporates, and the black hole era ends. The universe after objects. What comes after? What happens when the last black hole is gone? The universe enters its final state, the dark era, or as some physicists call it, the era of eternal darkness. No stars, no black holes, no objects of any kind. Just scattered particles, electrons, positrons, photons, neutrinos, spread across an infinitely expanding space. And time, endless, empty time, stretching forward without limit, forever. The question of forever. Here's something that might comfort you, or terrify you, I'm not sure which. The dark era has no end. There's no next era, no new phase, no eventual change. The universe will remain in this state forever. Infinite time. Every moment we've discussed so far, every era, every transition, every unimaginable span of years, all of it together is nothing compared to what comes after. Because what comes after is nothing. Forever. The Dark Era isn't a period in the universe's history, it's the universe's eternal state, its final condition, the way things will be for all remaining time. And time has no remaining limit. We'll explore the Dark Era more in the next section, but for now, let that sink in. The universe's story doesn't end. It just empties out and continues and continues. And so we arrive. The Dark Era, the final state of the universe. Not a chapter in cosmic history, but the end of history itself, the eternal afterward, the forever that follows everything. No stars have shone for 10 to the 100 years. The last black hole evaporated long ago, so long ago that the time since then already exceeds all the time before. What remains is almost nothing. Scattered particles, photons, electrons, positrons, neutrinos, spread across a universe so vast, so expanded that the distance between any two particles exceeds anything we can imagine. Darkness, cold, emptiness, forever. The shape of nothing. Let me try to help you picture this. In the dark era, the observable universe, which today spans about 93 billion light-years, will have expanded to incomprehensible dimensions. The expansion never stops. Space keeps stretching and stretching and stretching. By 10 to the 100 years, the observable universe will be so large that we'd need new mathematics just to write down its size. And within that unimaginable volume, almost nothing. The average density of the universe will be so low that you could travel for distances exceeding the current size of the cosmos and never encounter a single particle. Think about that. You could journey for 93 billion light-years, the entire diameter of today's observable universe, and find nothing. No particle, no photon, no trace of anything. Just space. Empty space. Expanding forever. The temperature of the end. And it's cold. So incomprehensibly cold. We've talked about temperatures approaching absolute zero, but in the dark era, the universe reaches temperatures so close to zero that they challenge our ability to express them. The cosmic microwave background, currently 2.7 Kelvin, will have cooled to perhaps 10 to the minus 30 Kelvin or less. At these temperatures, even quantum mechanics slows to a crawl. Particles barely move. Interactions almost never happen. The universe is frozen in a state of near-perfect stillness. Not quite absolute zero, that's forbidden by quantum mechanics, but so close that the difference is meaningless for any practical purpose. Nothing happens. Nothing changes. Time passes, but time is empty. Does time still mean anything? This raises a profound question. If nothing happens, does time still exist? Philosophers and physicists have debated this for centuries. Is time real, or is it just a way we measure change? If there's no change, is there still time? In the dark era, this becomes more than an academic question. With no events, no interactions, no observers, time becomes strange. 1 trillion years might pass, but with nothing to mark the passage, what does that mean? Is there a difference between 1 trillion years of nothing and 1 trillion years of nothing? In some sense, perhaps not. The dark era might be experienced, if experience is even possible, as a single, endless, unchanging moment. Or it might not be experienced at all, just existence without awareness. Forever.
Quantum possibilities. But here's where things get interesting. Even in the dark era, the universe isn't completely static. Quantum mechanics ensures that there's always a tiny amount of activity. Virtual particles still pop in and out of existence. Quantum fluctuations still ripple through the fabric of space. The vacuum itself is never perfectly still. And on truly vast timescales that make 10 to the 100 years look like an instant, incredibly rare events can happen. What kind of events? Well, almost anything.
Boltzmann brains. Here's a disturbing thought experiment. Given enough time, random quantum fluctuations can create anything. A particle, an atom, a molecule, a brain. Wait, what? It's called the Boltzmann brain problem, named after the physicist Ludwig Boltzmann. The idea is this. If you wait long enough, random fluctuations will occasionally create organized structures out of chaos. It's fantastically unlikely for any given moment, but fantastically unlikely doesn't mean impossible. And with infinite time, even the impossible becomes certain. So theoretically, random quantum fluctuations could assemble, purely by chance, a functioning brain, complete with neurons, memories, and consciousness. This brain would flicker into existence, experience a moment of awareness, and then dissolve back into chaos. A Boltzmann brain. The timescales involved are absurd. We're talking about 10 to the 10 to the 50 years or more, numbers so large that writing them out would take more space than the observable universe. But in the dark era, there's nothing but time. Infinite time. So will Boltzmann brains actually form? Some physicists take this seriously. Others think it's a sign that our understanding of physics is incomplete. The question remains open. But the possibility raises haunting questions about consciousness, existence, and what it means to be real. The fate of space itself. And what about space? Will it keep expanding forever? Current evidence suggests yes, the universe is expanding at an accelerating rate driven by dark energy. If dark energy remains constant, and we have no reason to think it won't, then space will keep stretching forever. But some theories suggest other possibilities. Perhaps dark energy will strengthen over time. In this scenario, called the Big Rip, the expansion would eventually tear apart everything: galaxies, stars, planets, atoms, space itself ripped to shreds. But most physicists consider this unlikely. The more probable fate is simply endless expansion, space stretching forever, particles drifting farther and farther apart, temperature dropping asymptotically towards zero, forever. Vacuum decay. There's one more possibility we should mention. Some physicists believe that our universe might be in a false vacuum, a state that seems stable but actually isn't. If this is true, then at any moment a bubble of true vacuum could form. This bubble would expand at the speed of light, destroying everything in its path. Not destroying in the sense of breaking apart, but destroying in the sense of rewriting the fundamental laws of physics. Within the bubble, particles might not exist as we know them. Matter might be impossible. Life certainly would be impossible. If a vacuum decay bubble formed, we'd never see it coming. It would arrive at the speed of light, and we'd simply cease. Could this happen in the dark era? Possibly. If it does, it would bring a kind of end to the universe. Not an end of existence exactly, but an end of the universe as we know it. But this too is uncertain. The dark era might simply continue, forever, unchanging, eternity without end. And so we're left with this vision. The dark era, eternal darkness, near absolute cold, scattered particles drifting through infinite space, no stars, no planets, no life, no events, no change, no history, just existence, bare, minimal existence, stretching forward without limit. A trillion years pass, a trillion years, a Google years, numbers beyond numbers, and still the dark era continues, because there's nothing to end it. Nothing can change. Nothing can happen. Nothing. Forever. That's the fate of the universe. That's what awaits at the end of all things. Unless something finds a way. We've painted a bleak picture. Stars dying, black holes evaporating, the universe fading into eternal cold darkness. But humans, and presumably any intelligent beings, don't accept endings easily. We fight, we adapt, we find ways. So let's ask the question that any conscious being would ask faced with the death of everything. Could anything survive? Could intelligence, could consciousness, could life in any form persist into the far future? Could the last thought ever be thought, be delayed indefinitely? Civilizations around black holes. Let's start during the black hole era. The stars are gone, the universe is dark, but black holes remain for trillions upon trillions of years. Could a civilization survive around a black hole? Surprisingly, maybe. Black holes aren't just gravity wells, they're sources of energy. A spinning black hole, called a Kerr black hole, carries rotational energy, and that energy can be extracted. The physicist Roger Penrose described a process, the Penrose process, by which objects falling into the ergosphere of a spinning black hole can emerge with more energy than they went in with. The black hole slows down slightly, and the difference is carried away as usable energy. A civilization could, theoretically, live off this process, extracting energy from a spinning black hole, using it to power computers, life support, whatever they need. The black hole would slowly spin down, but the energy available is enormous, potentially enough to power a civilization for eons. And there is another source, Hawking radiation. As the black hole evaporates, it emits radiation. A very advanced civilization might be able to capture and use this radiation. They could build a shell around the black hole, a Dyson sphere of sorts, collecting every photon of Hawking radiation. It's not much energy. Hawking radiation from a supermassive black hole is incredibly faint, far dimmer than starlight, but it's something. And with incredible efficiency, technology we can barely imagine, it might be enough. But here's the problem. Even if you can extract energy, you can't beat thermodynamics. Every computation, every thought, every process requires energy and produces waste heat. The second law of thermodynamics demands it. In a universe that's cooling toward absolute zero, you can't get rid of waste heat. There's nowhere for it to go. Everything around you is already as cold as your heat sinks. So you'd have to think slower, much slower. As the universe cools, any surviving minds would have to operate more and more slowly, stretching their thoughts across longer and longer timescales. Freeman Dyson explored this in a famous paper. He suggested that conscious beings could survive indefinitely by hibernating more and more, thinking less and less frequently, matching their energy use to the available temperature difference. A thought that takes a microsecond today might take 1 billion years in the far future. But it would still be a thought, consciousness persisting. Subjectively, the being might not notice any difference. Each thought would feel instantaneous, but objectively, eons would pass between them. Downloading consciousness. Another possibility, abandoning biology entirely. Organic life is fragile. It requires warmth, chemicals, energy gradients. It's not suited for the far future. But what if consciousness could be transferred to something more durable? A computer, or something stranger, quantum states preserved in the structure of space-time itself. This is speculative, of course. We don't know if consciousness can be uploaded or transferred. We don't know if it's possible to preserve subjective experience in a non-biological substrate. But if it is possible, a digital consciousness might survive where biological life cannot, operating on minuscule energy, thinking across vast timescales, persisting into the black hole era and perhaps beyond. The last civilizations. Let's imagine them. The last civilizations. They've survived the death of the stars. They've retreated to black holes. They've uploaded their minds, slowed their thoughts, adapted to the cooling universe. They exist in a state we can barely imagine. Thoughts spanning millennia, memories stretching across eons, time meaning something completely different than it means to us. What would they think about? Everything, perhaps. With essentially infinite time, from their subjective perspective, they could contemplate every possible idea, solve every solvable problem, create every possible work of art. They might simulate entire universes in their computers, run through every possible history, experience every possible life. They might become, in a sense, gods. Not gods of creation, the universe is dying around them, but gods of experience, beings who have thought every thought that can be thought. The final problem. But even these beings face limits. Eventually, the black holes will evaporate. The last source of energy will disappear. When that happens, what becomes of the digital minds, the uploaded consciousnesses, the final civilizations? They could try to operate on the diffuse energy of Hawking radiation from the evaporating black hole, slowing their thoughts further and further as the energy dwindles. Perhaps they could stretch their last thoughts across the entire remaining lifespan of the black hole, a single, final contemplation lasting billions of years. But when the black hole is gone, there's no more energy to extract, no more temperature difference to exploit. Nothing. The last thought. So here's the question. What is the last thought ever thought? The final conscious experience in cosmic history? Maybe it's a memory, a recollection of some ancient time when stars still shone and the universe was young and warm. Maybe it's gratitude, an appreciation for existence itself, however brief or long. Maybe it's curiosity, even at the end, wondering what comes next, even if the answer is nothing. Maybe it's peace, acceptance, a letting go. We don't know. We can't know. But somewhere, somewhen, in the far future, a mind will experience its final moment of awareness. The universe will contain one last flicker of consciousness, and then silence. Or maybe not. But here's a wild possibility. What if the universe doesn't end in eternal darkness? What if something else happens? Some cosmologists speculate about a big bounce, the idea that a contracting or flat universe might somehow trigger a new Big Bang. Others propose that quantum fluctuations in the far future might spontaneously create new inflationary regions, baby universes budding off from the old, dying cosmos. Others suggest that black holes might be seeds for new universes, that inside every black hole, a new space-time is born. If any of these are true, then the dark era might not be the end. It might be a transition, a long, cold sleep before a new awakening, the universe dying so that new universes can be born. The cycle possibility. Imagine that. The stars die, the black holes evaporate, the universe goes dark and cold. And then, after incomprehensible spans of time, something happens. A quantum fluctuation triggers inflation. Space expands exponentially. Energy floods the new region. A new Big Bang. New particles, new forces, new stars, new life eventually, new minds, new beings who will one day look up at their sky and wonder about the beginning, never knowing that they're not the first, that this has all happened before, that the cycle continues. This is speculative, highly speculative. We have no evidence for cosmic rebirth, but it's possible, and possibility in an infinite universe is a kind of hope.
What we don't know. The honest truth is, we don't know how the story ends. We can project current physics forward. We can calculate what happens if dark energy remains constant, if protons decay, if black holes evaporate, but physics is incomplete. We don't have a theory of quantum gravity. We don't fully understand dark energy. We don't know if new physics might emerge at energy scales or time scales we haven't yet explored. The far future might be stranger than we can imagine. There might be escape routes we haven't thought of, possibilities that our current science can't see. Or there might not be. Maybe the dark era is truly the end. Maybe consciousness has a finite lifespan, and when it's over, it's over. We don't know. And maybe that's okay. We've traveled so far together. from the light of present stars to the death of the last sun, through the long twilight of the degenerate era, past the evaporation of black holes, into the eternal darkness beyond. We've seen the universe end, not with a bang, but with a whisper, not in fire, but in cold. And now, we come back to this moment, this breath, this heartbeat. Because in the end, that's what all of this is about. Why this matters now. You might wonder why think about this at all. The death of the stars is so far in the future that it has no practical relevance to our lives. The degenerate era, the black hole era, the dark era, none of us will ever experience them. Our descendants, however far forward you project, will be gone before the last stars die. So why contemplate such things? Because perspective changes everything. When you understand the full timeline of the universe, when you truly grasp how brief and precious the stelliferous era is, something shifts inside you. The small worries that consume our days begin to seem smaller. The beauty of ordinary moments begins to seem more vivid. The miracle of existence, the fact that anything exists at all, that you exist at all, becomes almost unbearably precious. The preciousness of now. Right now, stars are shining. Not metaphorically, literally. Right now, nuclear fusion is converting hydrogen into helium in the cores of billions of stars. This won't always be true. One day, it will stop. The fusion will end. The light will fade. But not yet. Right now, you are alive. Your heart is beating, your lungs are breathing, your neurons are firing. You are aware, conscious, experiencing this moment. This won't always be true either, but not yet. Right now, the universe contains life, intelligence, beings who can wonder and question and love and dream. This is temporary. The cosmic window for life is open now, but it will close. But not yet. Right now is all we have, and right now is magnificent. Beauty in impermanence. There's a Japanese aesthetic concept called mono no aware. It roughly translates as the pathos of things or an awareness of impermanence. It's the bittersweet feeling you get when you see cherry blossoms falling. Not sadness exactly, but an appreciation of beauty that's deepened by the knowledge that it won't last. The falling petals are more beautiful because they're falling. The sunset is more beautiful because darkness will follow. The moment is more beautiful because it will pass. The universe is more beautiful because it will die. Mono no aware. The stars are shining now. They won't always shine, and knowing this, truly knowing it, makes their light more precious. You are alive now. You won't always be, and knowing this, truly knowing it, makes each breath more valuable. Not morbid, not depressing, beautiful. Heartbreakingly, exquisitely beautiful. What matters? If the universe ends in eternal darkness, what matters? This is perhaps the deepest question humans can ask. Some might say, nothing matters. If everything is temporary, if everything ends, if the cosmos itself will forget us, then what's the point? But I think that's backwards. Meaning isn't something the universe gives us, it's something we create. Love matters because we experience it. Kindness matters because it touches real beings. Art matters because it moves real hearts. Truth matters because it illuminates real minds. These things don't need to last forever to be real. A flower doesn't need to be eternal to be beautiful. A life doesn't need to be infinite to be meaningful. The universe doesn't need to remember us for our existence to have mattered. We matter now, to ourselves, to each other, and that's enough. Cosmic humility. The far future teaches us humility. We are small. Our planet is a speck. Our sun is ordinary. Our galaxy is one among hundreds of billions. Our era is a brief flicker in cosmic time. Everything we build will crumble. Everything we achieve will be forgotten. The universe will go on without us, and eventually, the universe itself will fade. This could be crushing, but it can also be liberating. If nothing is permanent, then we are free. Free from the burden of cosmic significance. Free from the pressure to build empires that last forever. We can simply live. Love the people near us. Create beauty where we can. Ease suffering where we find it. Appreciate the astonishing improbability of our existence. We don't need to justify ourselves to eternity. We only need to be here, now, fully present. The gift of consciousness. And there's one more thing. For a brief moment in cosmic history, this moment, the Stelliferous Era, the universe is conscious. Through us, and perhaps through other beings on other worlds, the cosmos knows itself. Stars are balls of plasma undergoing nuclear fusion. They don't know they're beautiful. Galaxies are collections of stars held together by gravity. They don't know they're magnificent. But we know. We look at the stars and feel wonder. We contemplate the galaxies and feel awe. We think about the far future and feel something. Sadness, maybe, or reverence, or a strange, quiet peace. The universe has produced beings who can appreciate it. Whatever happens in the far future, that has happened. That is real. The cosmos has, for a brief, shining moment, become aware of itself. And that awareness is you.
Resting now. Close your eyes. Let your body relax. Feel the weight of your limbs, the softness of the surface beneath you. You've been on a long journey tonight, trillions of years into the future, past the death of stars and the evaporation of black holes, into the darkness at the end of time. But now you're home, here, in this moment, in this body. The stars are still shining outside your window. Even if you can't see them, they're there, burning, fusing, sending their light out into the cosmos. And you're here, breathing, alive. Part of the brief, precious epoch when the universe is bright.